Section 10.2 is infinite series. Before I talk about series, I want to remind you what we just said about sequences. If we had a sequence of numbers, we would just express that if we were expanding it as a sub 1, a sub 2, a sub 3, so forth and so on. And we would just list the terms with a comma separating the terms. In a series, we use this notation. And it looks similar, but it's not. This is a capital sigma, a Greek letter sigma, and it means to add the terms together. N is what we would call the index of our series, and then 1 would be the lower bound, and then let's say this went only to 5. 5 would be the upper bound. And if I expanded this out, what that means is I would write, starting with my lower bound, a sub 1, sigma means add the terms, and then until I get to my upper bound. So that would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and plus a sub 5. That's what this series would look like if I expanded it out. This would be a finite series because my upper bound had a definite stopping point. In 10.2, we're going to be looking at infinite series. And an infinite series just replaces that upper bound with an infinity. When you're expanding out an infinite series, you're going to put this ellipsis ... at the end to show that it's going off to infinity. So the sum of an infinite sequence of numbers is going to be called an infinite series. If I were to look at this, is there a way that I could write this expanded series using sigma notation? And there is, because this looks like powers of 2 in the denominator. So I would say this is 1 over 2 raised to the n, starting at n equals 0. Now with the sequences, I told you they always start with n equals 1, and that's true. But with a series, you can define the starting point based on what your lower bound is. If I were to start this sequence at n equals 0, 1 over 2 raised to a power of 0 is 1. And then 1 over 2 to the first, 2 second, 2 to the third, 2 to the fourth, so forth and so on. So this is a way that I could represent this infinite sum using sigma notation. Some of your homework problems will give you an expanded series and ask you to write it in sigma notation. Now this representation is not unique. I could also write this as the sum started at n equals 1. This would be 1 over 2 raised to the n minus 1. Don't these two things represent the same thing when I expand it out? Series representation is not unique. It can change depending on what you define your starting point to be. Now what that means is we're going to be adding the terms from what was previously our sequence together. And when we do that, we generate what's called partial sums. So if this is my series, and if I look at the first partial sum, it's just the first number that I get here, and that value is 1. I could probably express that as 2 minus 1, because in a minute I'm going to show you how we determine what this series converges to. The second partial sum would be s sub 2. It's just the sum of the first two numbers, and that's 3 halves. Well, if we notice, that's going to be 2 minus a half, gives me 3 halves. The third partial sum, I just add together the first 3 terms, and that gives me 7 fourths. Well, that's 2 minus a fourth. And then if I look at the nth partial sum, that would be every term here, and then plus 1 over 2 to the n minus 1, and that value is going to be equal to this, which I could express as this. What that tells me is that this infinite series is approaching the number 2. So as the lengths are added one at a time, the sum approaches 2. Not any one of these sums, the value that any of these partial sums is going to be exactly equal to 2. It's the limit as n goes to infinity that's actually going to be equal to 2. So given a sequence of numbers, an expression of the form a sub 1 plus a sub 2, so forth and so on, is an infinite series as long as it's going off to infinity. You're adding an infinite number of terms together. The sequence defined by the partial sums is going to be equal to the sum k equals 1 to n of a sub k, where n would be the nth partial sum. The index on this series would be k now. That would be the variable. That's why we used an a sub k. This is the sequence of partial sums of the series. And then if we look at the limit as n goes to infinity, we would get the sum of that infinite series. The series converges and we can find that limit, which would be what that series is equal to. It's what it converges to. This first series is called a geometric series. It says if the absolute value of r is less than 1, the geometric series a plus a times r plus ar squared plus so forth and so on, ar to the n minus 1, converges to a over 1 minus r. It's saying that this series converges if the absolute value of r is less than 1, meaning r has to be a proper fraction. This is how you would write the series if we start with n equals 1. It's a times r to the n minus 1. On your cheat sheet, I've written the series starting at n equals 0, and that's just a r to the n. That geometric series is going to be equal to a over 1 minus r. That's how you would find the sum of this infinite geometric series. That's true only if r is a proper fraction. It could be positive, it could be negative, it doesn't matter, but it has to be a proper fraction. Now I want to show you that this series that I have written in red here is the exact same as this series that I have written in blue. So this is going to start at n equals 1, go to infinity, and then this is a r to the n minus 1. If I were to expand this out, when n is equal to 0, r raised to a power of 0 is 1, and 1 times a is a. Plus, when n is equal to 1, I get a times r. Plus, when n is equal to 2, I get a r squared, so forth and so on. Now let's expand the terms in this blue series. Starting with n equals 1, 1 minus 1 is 0, so that's just going to give me a. When n is equal to 2, 2 minus 1 is 1, so that's just a times r to the first. When n is equal to 3, we get 3 minus 1 is 2, so that's going to be a r squared, so forth and so on. You see how these terms line up, they match up. That's why I told you series representation is not unique. So you can write your convergent geometric series using the index starting at 0, or if you start the index at 1, this has to be raised to the n minus 1. Either way, the sum is going to be equal to a over 1 minus r, provided that r is a proper fraction. You can find the series cheat sheet if you lose yours in Brightspace underneath week 10. And if you look down here for the geometric series, I give you the test for geometric series, what the series looks like, the conditions for convergence and divergence, and then what the sum is equal to. So that's where you would look on your series cheat sheet. In example 1, I've asked you to find a formula for the nth partial sum of the series, and I've given it to you as an expanded series, and then use it to find the sum of the series, if the series converges. So the first thing I notice is every term in this series has a 4 in it. So what I'm going to do is I'm going to start by factoring out that 4. And when I factor a 4 out of this term, I'm left with 1. And when I factor a 4 out of the next term, I'm left with 1/6. When I factor the 4 out of the next term, I'm left with 1 over, that's 6 squared. And then 6 cubed is 216, so this is 1 over 6 to the third. And then I get 1 over 6 to the n minus 1. The next term would be 1 over 6 to the n, and it goes on and on and on. So looking at the geometric series, that's what this looks like. I have a constant, a. I have 1/6 raised to a power of n. So it looks like this would be a geometric series where a is equal to 4 and r is going to be equal to 1/6. I want to write my geometric series using the pattern that I give you on the cheat sheet. So that looks like this. It's the sum n equals 0 to infinity of a r to the n. And that's going to be equal to a over 1 minus r. So my geometric series I can write as the sum n equals 0 to infinity of 4 times 1/6 raised to a power of n. Does this geometric series converge? What are the conditions for convergence on the cheat sheet? We're told the absolute value of r has to be less than 1. Our r here is 1/6. That's less than 1. Therefore, this series converges. This series converges since r is equal to 1/6. And we were told that if the series converges, find the sum. There's very few series that we're going to be able to find the sum for. The geometric series is one of them. So the sum is going to be equal to a over 1 minus r. But we were told, or we figured out, that a is equal to 4, and then that's 1 minus 1/6. When we do the arithmetic on this, this is going to give us 4 divided by 5/6, and that's going to be equal to 4 over 1 times, flip the fraction, so that would be 6/5, and this series is going to be equal to 24/5. That's what the series converges to. Example 2, we're asked to write out the first few terms of the series and then find the sum. So if I were to expand this series out, the first thing I'm going to do before I expand it is I'm going to rewrite this using a property of exponents that hopefully you do remember. It's a distributive property of exponents. If we have a to the n over b to the n, I can rewrite that as a over b to the n. Do y'all remember that distributive property of exponents? We're going to use that to rewrite this series because I think it's going to make it easier to see what the terms are. So since -1 is raised to a power of n and 11 is raised to a power of n, I'm going to rewrite this as -1 over 11 raised to a power of n. And when I expand this out, that's going to give me -1 over 11 to the 0, plus -1 over 11 to the first, plus -1 over 11 to the second, plus -1 over 11 to the third power. And that's enough terms, I think. And when I simplify this, anything raised to a power of 0 is 1, and then -1 over 11, and then plus 1 over 11 squared is 121, minus, because you cube a negative, it's negative. So when we expand this series out, this is what it's going to look like. And then we're asked to find the sum of the series. Well, we notice that this is a geometric series. It's easier to recognize that it's going to be a convergent geometric series here with it written like this instead of like this. This is a geometric series, and what is a going to be equal to? If there's no number there for a, we say that a is going to be equal to 1. R is going to be equal to -1 over 11. Does this series converge? Remember, this is what we're looking at. This series is going to converge if the absolute value of r is less than 1. The absolute value of -1 over 11 is 1 over 11. 1 over 11 is less than 1. So we say that this is a convergent geometric series, and the sum is going to be a over 1 minus r. Since I have to find the sum, I'm going to use that formula, a over 1 minus r. A, we said, was 1, and r is equal to -1 over 11. 1 plus 1 over 11, it gives me 12 over 11. And so that means, when I take care of the arithmetic, this is going to be 11/12. The sum of this convergent geometric series is 11/12. The question was, can we use the cheat sheet on the test? And the answer is yes. Now there's another way that we can use the geometric series, and that's for expressing a repeating decimal as the ratio of two integers. Because the ratio of two integers is actually the sum of a geometric series. And you say, well, how is it the sum of a geometric series? It's a ratio of two numbers. The sum of a geometric series is the ratio of two numbers. So they want us to express this as a fraction. Well, the easy way to do it is to notice that these numbers, 13, keep repeating over and over and over. So that means that I could rewrite this as 13 over 100 plus 13 over 100 squared, because that gives me 4 decimal places. It puts me out here to the 4th, plus 13 over 100 cubed. I'm using 100 because the first number went out to 2 decimal places. And this would repeat on and on and on. What would the next term be? 13 over 100 to the 4th. Until I get out to the nth term, and that would be 13 over 100 raised to a power of n. I'm going to factor the 13 over 100 out. If I factor a 13 over 100 out, that first term is going to be 1. That next term is going to be 1 over 100 to the first power because I took one of them out. The 13 I factored out and one of these hundreds I factored out, and that's going to leave me 1 over 100 squared. The 13's factored out, one of those hundreds is factored out, so I'm left with 100 raised to the third power, and then this would be 1 over 100 raised to the n minus 1, so forth and so on. So I could express this as a geometric series starting at 0, where a is equal to 13 over 100 times r, which is 1 over 100 raised to a power of n, starting with n equals 0, because this is my a, and that's r to the 0. Well, this is what I get when n is equal to 0, n is equal to 1, n is equal to 2, when r is equal to 1 over 100. Because r is equal to 1 over 100, that means that I have a convergent geometric series. And how do you find the sum of the geometric series? It's a over 1 minus r. Well, a we said was 13 over 100 divided by 1 minus 1 over 100. And that's going to be 13 over 100 divided by 99 over 100. And that, when I flip and multiply, that's going to give me 13 over 100 times 100 over 99. And the hundreds are going to cancel out, and I'm just left with 13 over 99. That would be the ratio of two integers. We can check that to see if we got the right answer just by dividing 13 by 99. And we see that we do get the repeating decimal. You should always be able to tell if you got this answer correct just by using your calculator to divide these two numbers and see if you get what you started with. But that's how you would express a repeating decimal, as the ratio of two integers. Now I'm going to insert another example in here because I forgot to put an example like this in my lecture notes. Here's an extra example. Find the sum of the series that goes from 2 to infinity of 2 times 1/7 raised to a power of n. The first thing you need to notice is that this is a geometric series. What is a equal to here? 2, and r is equal to 1/7. We know that if we have a series that goes from 0 to infinity of ar to the n, that's going to be a over 1 minus r. We've just worked a couple of problems there. The problem is, our series doesn't start at 0, it starts at 2. So the question is, how are we going to handle that? Let's do some investigating. So if I have a series and I want to expand it, a geometric series starting at n equals 0. When I expand this, I'm going to get a plus, this is when n is equal to 0. When n is equal to 1, I get ar. When n is equal to 2, I get ar squared. When n is equal to 3, I get ar to the 4th. And when n is equal to 5, I get ar to the 5th. And then my nth term would be ar to the n. And we know, because this is a geometric series, that sum is going to be equal to a over 1 minus r. Well, what happens if our series starts at 2? Well, let's look at n equals 2 to infinity of a r to the n. And when we're starting at 2, my first term is going to be a r squared. My next term will be a r cubed. My next term will be a r to the 4th, all the way out to a r to the n. And the question is, what is this equal to? Well, notice these terms start matching up right here. And I could keep going. And so this goes out to infinity. So the sum of this series is going to be the same as the sum of this series, a over 1 minus r, but I'm missing these first two terms when n was equal to 0 and n is equal to 1. So what I have to do is subtract off those two terms that are missing from this sum. So that's going to be minus ar to the 0 minus ar to the 1st. If your series starts at any number other than 0, you have to subtract off the terms from the sum that start at 0, where n is equal to 0 and n is equal to 1, until you're left with your index n equals 2. So knowing that now, let's look at the problem that I gave you. I want you to find the sum of this series. Well, the sum of that series is going to be equal to a over 1 minus r, but what do I have to subtract? I have to subtract what I got when n was equal to 0, and I also have to subtract what I got when n was equal to 1, because our series starts at n equals 2. In this series, we said a was 2, so that's 2 divided by 1 minus, and we said r is a 7th. When n is equal to 0, I'm just left with 2, and then minus 2 times 1/7, which is 2/7. So that's going to give us 2 divided by 6/7 minus 2 minus 2/7. And that's going to be equal to, this is why God gave us calculators. Let me expand it out. So that's going to give us 2 over 1 times 7 over 6 minus 2 minus 2/7. And so 2 goes into 6 3 times. Okay, 7/3 minus 2 minus 2/7. If I get a common denominator, that common denominator is going to be 21. But if I use my calculator, I'll get the answer quicker. And that's going to be 1 over 21. And that would be what that sum is equal to. It was just pointed out. I forgot the AR cubed, so I need to change my exponents here. This would be R cubed. This would be R to the 4th. So now it all matches up the way it's supposed to. Thank you. Does this make sense, how you're going to find the sum of a geometric series if the index starts at anywhere other than 2? Yes, good. The last type of series we're going to look at is a telescoping series. And I believe the telescoping series are on your cheat sheet as well. Let's look there right quick. Yes, the telescoping series. They can be written as the sum of the difference of two sequences. And they're going to converge if the limit of the nth term is equal to some number. The sum would be b sub 1 minus that limit. This is more confusing than what I'm going to show you here in the notes. So here we're asked to find a formula for the nth partial sum of the series and use it to determine if the series converges or diverges. What we're going to do with the telescoping series, and you can tell you have a telescoping if you have the difference in between here. We're going to expand out all of these terms until we have two groupings that both terms are going to cancel out. So let me show you what I'm talking about. We're going to start this series with n equals 1. And so we plug in a 1 in place of n, and that's going to give us 3 over 1 minus 3 over 2 plus, and then when n is equal to 2, we're going to get 3 over 2 minus 3 over 3 plus, when n is equal to 3, that's going to give us 3 over 3 minus 3 over 4. When n is equal to 4, that's going to give us 3 over 4 minus 3 over 5 plus, so forth and so on. It's going off to infinity. So then we look for things that are going to cancel. Well, here I have a negative 3/2 and a positive 3/2 that are going to cancel out. Here I have a negative 3/3 and a positive 3/3 that are going to cancel out. Here I have a negative 3/4 and a positive 3/4 that are going to cancel out. And if I were to keep expanding this, I would have a 3 over n minus 1 minus 3 over n plus, and then the next term, that would be my n minus 1 term. And then for my nth term, I would get 3 over n minus 3 over n plus 1. Well, we can see that this term is going to cancel with that term. That term would have canceled with the one that came before. And what I'm left with is this last term. If the limit as n approaches infinity of that last term that you're left with is equal to 0, then the series is going to converge. So when you're canceling things out, look at the last term that doesn't cancel. If the limit as n goes to infinity of that last term is 0, you're in business. Everything is going to cancel out here. This negative 3/5 would cancel out with the first positive term in the next term. The only number that I'm left with that didn't cancel out is 3. So we would say that this series is equal to 3. When you have a telescoping series, expand the series out, cancel where you can, and as soon as you have a pairing here, I could have stopped right here because at that point, both of these numbers canceled with the numbers over here. Once you have a set of parentheses where both terms cancel, then you're done. You can stop expanding. Any numbers that are left over that didn't cancel out on the left are going to be your answer. This one just happened to have one number. Sometimes you can have 2 or 3 numbers that you have to add together where the terms don't cancel out. In the next problem, example 5 asks you to use partial fractions to find the sum of this series. There's only 2 types of series that I'm ever going to ask you to find the sum for. One of them is geometric, the other one is telescoping. This problem is clearly not geometric, which means it must be telescoping. So we have to use the skills we learned when we did partial fraction decomposition. So that means I'm going to set 8 over 2n minus 1 times 2n plus 1 equal to a over 2n minus 1 plus b over 2n plus 1, and I'm going to solve for a and b. So I'm going to multiply both sides of the equation by the least common denominator, and that's going to give me 8 equals a times 2n plus 1 plus b times 2n minus 1. If n is equal to 1/2, then this term is going to 0, and I get 8 is equal to 2a, which means that a is going to be equal to 4. And if n is equal to a negative 1/2, then I'm going to get 8 is equal to, this is going to be 0, and I get negative 2b, which means that b is going to be equal to negative 4. And what that means is that I can rewrite this series as the sum n equals 1 to infinity, because this series started at 1, so does this one. A we said is 4 over 2n minus 1 minus 4 over 2n plus 1. Now this is easier to recognize as a telescoping series. And how do we find the sum of the telescoping series? We're going to expand it out. Starting with n equals 1, we get 4 over 2 times 1 is 2 minus 1 is 1 minus 4 over 2 times 1 is 2 plus 1 is 3. When n equals 2, we're going to plug in a 2 in place of n, and that's going to give us 4 over 4 minus 1 is 3, so that's going to be 4/3 minus 4 over 5 plus, when n is equal to 3, we get 4/5 minus 4/7 plus, and I think we can stop here because I have a negative 4/3 that will cancel with the positive 4/3, a negative 4/5 that will cancel with the positive 4/5. So as n goes off to infinity, this last term is going to converge to 0. So that means that the sum of this telescoping series is going to be equal to 4. The next thing we're going to talk about is the nth term test for a divergent series. One reason that a series may fail to converge is that its terms don't become small. When we were evaluating sequences, we said that the sequence converged if the limit as n approaches infinity of the nth term was equal to some number. For a series, when we're adding terms together, the limit of that nth term has to approach 0 in order for the series to converge, because the series has to get small enough, fast enough for us to be able to find the sum as n goes off to infinity. Now, one word of caution is that Theorem 7 does not say that the series is going to converge if the sequence goes to 0. The terms of the sequence. This is not a test for convergence, it's a test for divergence. So when we use this test, we're checking to see if a series diverges. If we look at our cheat sheet here, the very first test listed is the nth term test, and it has no conditions for convergence because you can't use it to test to see if a series converges. You can only check to see if the series diverges. If the limit of the sequence, the terms of the sequence part of this series, is not equal to 0, then the series diverges. So the nth term test for divergence says that the series n equals 1 to infinity of a sub n diverges if the limit as n approaches infinity of a sub n either fails to exist or is anything other than 0. In example 6, we're told if the series converges, what is its sum? Well, if we expand out the terms in this series, starting at n equals 0, cosine of 0 is 1. When n is equal to 1, I would get cosine of 9 pi. 9 pi is odd, so that would be negative 1. If n is equal to 2, I would get cosine of 18 pi. 18 pi is on the positive x-axis, so that would give me positive 1. And then negative 1, and so forth and so on. This would just oscillate between 1 and negative 1. These terms would. So would this series converge? When we expand these terms out, this is not going to be equal to 0. So we would say then that the limit as n approaches infinity of cosine 9n pi, this limit does not exist because the terms are just oscillating between 1 and negative 1. Therefore, we would say that the series diverges by the nth term test. So because the limit didn't exist, we would say the series diverged by the nth term test for divergence. In part B, we're given the series n equals 0 to infinity of e raised to the negative n over 2. If the series converges, we're asked to find the sum. The only two series that we're able to find the sum for is the telescoping series and the geometric series. So if this does not diverge, then I need to either rewrite this as a telescoping or a geometric series in order to find the sum. So I'm going to start out by rewriting this series and get rid of the negative exponents. This is the same thing as e raised to the negative 1/2 times n. Remember, when you raise a power to a power, you multiply the exponents. So that means that I could rewrite e to the negative n over 2 as e raised to the negative 1/2 raised to a power of n. And what does that exponent of 1/2 do to something? When your power is 1/2, that means you're taking the square root. So when I rewrite this, I can rewrite this as 1 over the square root of e raised to the power of n by using these properties of exponents. What does this look like to you? Doesn't it look like a geometric series? What would r be equal to here? This looks like a convergent geometric series where a is equal to 1 and r is equal to 1 over the square root of e. E is approximately 2.81 something something something. Take the square root of 2 point something, you get 1 point something. 1 divided by 1 point something is a proper fraction, so that is going to be less than 1, and so this would be a convergent geometric series. Since our series starts at 0, that means that the sum is going to be equal to a over 1 minus r. So for this series, we would say that the sum is going to be 1 divided by 1 minus 1 over the square root of e. The question was, how did I get this, and what about the negative 1/2? Well, the negative 1/2 means that that e gets kicked into the denominator to make the negative exponent positive. What I'm using here is this is going to be equal to 1 over e to the positive 1/2 raised to the n, and e to the 1/2 was the square root of e. That's how I rewrote this. I had to use the exponent rule, where you raise a power to a power, you multiply the exponents, and then to make a negative exponent positive, you just move that term into the denominator. And a power of 1/2 is the same thing as the square root. That's how I got this. Now, because this is a convergent geometric series, I can say that the sum is going to be equal to 1 over 1 minus 1 divided by the square root of e. You do not want to leave your answer like this. You don't want a complex fraction in your answer. So the way to get rid of the complex fraction here is I can distribute a square root of e to the numerator and to the denominator. I'm going to distribute that across. And when I do that, that's going to give me the square root of e over the square root of e minus 1. And typically you don't want to leave a radical in your denominator. So what we would do is rationalize this by multiplying both the top and the bottom by the conjugate of the denominator. So that would be the square root of e plus 1 over the square root of e plus 1. Now I'm going to distribute this across here, and I'm going to FOIL this out. And when I do that, the square root of e times the square root of e is e, plus 1 times the square root of e is the square root of e. And then this is the difference of two squares, so I'm going to square the first term and then put a minus and square the last term, and this would be our final answer. This would be the sum for this convergent geometric series. All of the rules that applied for the limits are also going to apply for the sums. They also applied for the sequences. It says if we have the sum of a sub n equals some finite number a, and the sum of b sub n is equal to some finite number b if they are convergent series, then if I add two series together and I look at the sum of two series, I'm going to get the sum of what those series are equal to. And the difference of two series is equal to the difference of their sums. And the constant multiple. What rule is missing here? There's actually two of them, the product rule and the quotient rule. And the reason those aren't listed is because it gets very complicated whenever you're multiplying series together. Because when you multiply a binomial times a binomial like we did up here, you don't just multiply the two terms together. You've got to also take into account the outside and the inside terms. Well, if you have an equal number of terms in your series, the multiplication gets really, really complicated because you have to use the distribution property. So we don't list those here for these theorems. We're only going to use the sum, difference, and constant multiple rule for series. So every non-zero constant multiple of a divergent series diverges, and if the sum of a sub n converges and the sum of b sub n diverges, then the sum of a sub n plus b sub n and the sum of a sub n minus b sub n both diverge. What that means is divergent wins. It's like a trump card. You ever play spades and you have a trump card, spades or trump? You could have the highest card in another suit, but a two of spades will take it because it's a trump card. Divergence cannot be overcome. If either one of the series diverges, then the whole thing diverges when you're adding and subtracting series. And the last example we're going to look at in Example 7, these two problems are going to pull in a lot of different things that we learned in this section. So for part A, we're asked to find the sums of the following series. What I would want to do here is distribute this denominator and rewrite this. And because I was asked to find the sum, I'm hoping these are geometric series. When we distribute the denominator, that's going to give us 3 to the n minus 1 divided by 6 to the n minus 1 minus 1 over 6 to the n minus 1. If you want to get rid of that n minus 1, all you got to do is start this at 0. If n is equal to 1, 1 minus 1 is 0. So if I change my starting point from 1 to 0, I could rewrite this as 3 to the n divided by 6 to the n minus 1 over 6 to the n. I'm choosing to do that just because it's easier on the eyes. It's easier to look at if we don't have that difference in the exponent. Remember, I said series representation is not unique, so I can do this, rewrite this by changing the lower bound. Now we also have a distributive property of exponents. Another way that I could rewrite this is this would be equal to the sum of 3 over 6 to the n, because we have a distributive property of exponents, minus 1 over 6 to the n. And 3/6 reduces to 1/2. And I chose also to distribute that summation and just evaluate these as two separate geometric series, and then we're going to subtract the sums from each other. So for this first geometric series, A would be equal to 1 and R is equal to 1/2. For the second one, A is equal to 1 and R is equal to 1/6. And the sum of the geometric series is going to be A over 1 minus R, so that's going to give us 1 over 1 minus 1/2 minus 1 over 1 minus 1/6. And then just taking care of the arithmetic, that's going to give us 1 over 1/2 minus 1 over 5/6. And 1 over 1/2 is 2 minus, and this is going to be 6/5. And when we subtract that, we're going to get 4/5 for the sum. So the sum of the geometric series in part A is going to be 4/5. The question was, why did I write it like this? And the answer is because the sum of the geometric series is A over 1 minus R. For part B, clearly this is a geometric series. Well, I say clearly, but it may not be so clear. We may need to rewrite this in order to clearly see that this is a geometric series. So my constant term, what's not being raised to a power, is 4. And then that's being divided by 2 to the n, but another way to write that is 1 over 2 to the n. Or I could write that as 4 times 1/2 raised to a power of n. And you say, well, that 1 wasn't raised to a power of n, so why can you write it like that? Anybody thinking that? 1 raised to any power is 1. That's why I can rewrite this as 1/2 raised to a power of n. I write it like that because it's easier to see what A and R are equal to. So A is equal to 4 and R is equal to 1/2. And using the formula for the sum of a geometric series, we see that that sum is going to be A over 1 minus R. So that's going to give us 4 divided by 1 minus 1/2, which reduces to 4 over 1/2. And when we flip and multiply, that's going to give us 8. These are both convergent geometric series, and the sum for part A is 4/5, and the sum for part B is 8. And this wraps up section 10.2.